So you have parameters, and these parameters have to be estimated. And be careful that k is a time parameter. Do you remember how we define k? If you go back in your notes, you see that if you analyze the units of k, it's a time parameter. So how can we define k? There are some mathematical proofs in hydrology, which I'm not explaining in detail, that prove that k is related to the time of concentration of the catchment, which is understandable. But we are not much interested in that, because I already mentioned to you that even the time of concentration is something that is difficult to estimate. So, if your question was, how do we estimate these parameters, my reply would be by comparing simulated versus observed data. Again, we are talking of what? We are talking of parameter estimation. And parameter estimation is indicated in the literature with a plethora of terms, and I want to mention to you some of them. They are synonyms. So, parameterization, optimization, calibration, these are some terms that are used interchangeably, I hope my pronunciation is correct, like synonyms. And basically their meaning is to find the best value for the model parameters. The best value for the model parameters, plural, because in general models have more than one parameter. So, how it is performed? As I said, by comparing observed versus simulated river flows. Again, by comparing observed versus simulated river flows. Let me make an example. Suppose that you have an observed hydrograph, which looks like this one. This is observed. And then let's assume that you get you adopt a rainfall runoff model, like the linear reservoir, and you take a couple of values for the runoff coefficient and k. And then, just by trial and error, you make a trial with two values, like runoff coefficient 2.5 and k equal to what is your guess for the time of concentration. And let's suppose that you get an hydrograph that is like this. Okay, this is simulated. And then you say, this is not good. Look, usually you shouldn't get an hydrograph that is completely, or no, okay, you could. You could also get an hydrograph that is completely above the observed line or completely below. Because depends on the value of the runoff coefficient. So basically what you could do is just move by trial and error. So if you get an hydrograph like this, you could say, okay, let me try to change the runoff coefficient or change K and see if I can get to a better representation. And I said it's a trial and error, but indeed, once that you know a model, you can perform a guided search. For instance, the runoff coefficient is just a multiplier which shifts the whole hydrograph above and below. So it's just a shift because it's a multiplier. Instead, if you change K, you change the shape of the hydrograph. It's not just a shift. You change the shape. You can enlarge it or shorten it. Because K is related to the time of concentration, and therefore if you take a low value of K, you reduce the time of concentration, you reduce the base time of the hydrograph. If you increase K, you increase the base time of the hydrograph. And it's interesting, when we develop applications in R, it's interesting to notice in practice how this takes place. So basically, when you use a model, you should play with the model and understand what is the effect of tuning a given parameter. This means experience. Like, you use the linear reservoir and you perfectly know what happens to the hydrograph if you increase K. This is experience, which is not a synonym of age, as I already mentioned to you. It's just a matter of playing with the model, dedicating time to the model, understanding how it works. And therefore, based on your experience, if you get an hydrograph that is wrong, you can change the parameters according to experience and quickly converge to a better solution. This is a trial and error manual calibration. Manual, why manual? Because you change the parameters. You take the decision to change K rather than the runoff coefficient and how to change it. So it's called manual calibration, and it's a trial and error because you look at the result and you just decide how to move forward. Of course, this is not easy, especially if you have like 10 parameters in a model, then you know the possible combinations are many and many and many. So if you have just one parameter, it's easy. Try to increase it, try to reduce it, and that's it. And then you quickly understand if you need to reduce even more or increase even more. But already in the situation where you have two parameters, you know, possible combinations are 4. Increase, increase, reduce, reduce, increase, reduce, reduce, increase. 4 combinations. So it becomes a bit more complicated. If you have 3 parameters, 9 combinations, and etc. 9. Yeah, I think so. So basically, if you have a lot of parameters, this manual calibration is difficult to perform. And then there is an alternative which became very popular in the past 20 years, which is automatic calibration. It is the PC that makes the calibration for you. And in R, you have several algorithms which you can use to perform the automatic calibration. Okay, at this stage I will stop in a minute. I need to close the lecture at